we now discuss the solution of a problem from the section Permutations and Combinations, and the problem is on the counting the number of functions. This question has appeared in Joint Entrance Exam Main held on 27th July 2021 in the Shift 1. The problem is, let S be the set consisting of the elements 1, 2, 3, 4, 5, 6, 7. Then we have to find the number of possible functions f from S to S such that f of m into n is equal to f of m into f of n for every mn belongs to S and m into n belongs to S is equal to. So we have to find the number of functions f S to S which satisfies f of mn is equal to f of m into f of n for every mn belongs to n, and for such m comma n belongs to S such that m into n again belongs to S. That means you have to consider all mn's such that m into n also belongs to S for all m comma n coming from S. We will now discuss the solution of the problem in detail. We have given the set S consisting of the positive integers from 1 to 7. Now we want to count the number of functions f from S to S such that f of mn is equal to f of m into f of n for every mn belongs to S and m into n belongs to S. Note that f of mn, we have dropped the dot for multiplication and we write mn for m into n. F of mn is equal to, by definition, f of m into f of n, and f of m, f of n are positive integers from S and they commute, and that will be equal to f of n into f of m. Again use the definition of the function f, you will get f of nm. So f of mn is equal to f of nm, that means f is symmetric in m and n. Further, the functions which satisfies this condition, that is f of mn is equal to f of m into f of n for all mn belongs to S is called multiplicative functions. Anyway, this for such function f is symmetric in m and n. Now mn belongs to S, the product mn belongs to S for all mn belongs to S means the product mn is less than or equal to 7. That means the product mn belongs to S. And mn less than or equal to 7 for all m into m comma n belongs to S. This means 1 into n less than or equal to 7 for all n belongs to S. This happens for every n belongs to S. Suppose we take m is equal to 2, 2 into n will be less than or equal to 7 for only those n for which n is equal to 1, 2, 3. 2 into 1, 2 less than 7, 2 into 2, 4 less than 7, less than or equal to 7, 2 into 3, 6 less than or equal to 7, and 2 into 4, if you take it, 8, it is not less than or equal to 7. So from there onwards, nothing will work. So these are the ordered pairs, 1 comma n, 2 comma n. These are the ones for which this second condition is valid. Now if you take m is equal to 1, then f of mn, that is f of 1 into n, f of n is equal to f of 1 into n, and by definition f of 1 into f of n, true for all n belongs to S. Now f of n is here, and take take them to one side and take f of n common, then you will get f of n into f of 1 minus 1, and f of n is not equal to 0 for any n belongs to S. This implies f of 1 minus 1 is equal to 0. This implies f of 1 is equal to 1. So for such functions, f will take 1 onto 1 only. We continue in the next slide. We have f of 1 is equal to 1. If m is equal to 2, n is equal to 2, then f of 4 is equal to f of 2 into 2. By definition, f of 2 into f of 2. So, for what value of f of 2? F of 2 into f of 2 belongs to S. Suppose I take f of 2 is equal to 1. 1 into 1, 1 belongs to S. Yes. So, f of 2 is equal to 1 is possible. F of 2 is equal to 2 if I take it. 2 into 2, that is 4. 4 belongs to S. Correct. So, f of 2 is equal to 3 if I take it. 3 into 3 does not belong to S, because 3 into 3 is 9. Does not belong to S. So, from there onwards, f of 2 is not 3, not 4, not 5, not 6, not 7. So, only possibility is, this implies f of 2 is equal to 1 or f of 2 is equal to 2. So, thus the possible choices are branched out at this level R. Now, so this means f of 2 is equal to 1. If I take f of 2 is equal to 1, what will be f of 4? F of 2 into f of 2, that is 1 into 1, 1. So, in the second case, if I take f of 2 is equal to 2, f of 4 will be f of 2, 2 into 2, that is 4. So, that's the possibility. Next, if m is equal to 2, n is equal to 3, then f of 6 is equal to f of 2 into 3. And that will be, by definition, f of 2 into f of 3 belongs to S. Such things we have to consider. So, in our first case, f of 2 is 1. F of 2 is 1 if I take it. 1 into f of 3 belongs to S. What could be f of 3? F of 3 can be any value from 1 to 7. So, f of 2 is equal to 1. F of 3 will be any value from 1 to 7. So, in the second branch, f of 2 is equal to 2 if I take it. 2 into f of 3 belongs to S. What will be the value of f of 3? So, 2 into 1 belongs to S. 2 into 2, yes, 4 belongs to S. 2 into 3, 6 belongs to S. 2 into 4 does not belong to S. So, the value for f of 3 can be 1, 2, 3. So, when f of 2 is 1, f of 3 can take any value from 1 to 7. When f of 2 is 2 in the second branch, f of 3 can take 1, 2, 3. Next, now let us see, so far what is that we have done? F of 1 is 1, it is common to both the branches. F of 2 is 1, and f of 3 is 1 to 7. F of 6 is now f of 3, or f of 2 is f of 2. F of 3 is 1 to 3. F of 6 is f of 2 into f of 3, that is 2 times f of 3. So, that is the situation so far. Now, f of 5, if I take it, f of 1 into 5, that is equal to f of 1 into f of 5, and f of 1 is 1, and f of 5 is less than or equal to 7. Therefore, f of 5 can be 1, 2, 3, 4, 5, 6, 7, any value it can take. So, and similarly for f of 7, any value it can take from 1 to 7. So far, what is the situation? So, we have two branches, write down the two branches. F of 1 is 1, f of 2 is 1, right? F of 3 is 1 to 7, f of 4 is 1, f of 5 is any value from 1 to 7, f of 6 is f of 3, f of 7 is any value from 1 to 7. This is in this branch, first branch. Or branching out the second. F of 1 is 1 common, F of 2, 2, and F of 3, 1 to 3, F of 4 is 4, F of 5, 1 to 7, F of 6 is 2 into F of 3, F of 7, 1 to 7. These are the two branches what we have. So let's now summarize this in the next slide. We have F of 1 is 1. Now all those values to the first branch I have written, and that I will tabulate. So F of 1 is 1, F of 2 is 1, F of 3 is 1 to 7, F of 4 is 1, F of 5 is 1 to 7, F of 6 is F of 3, F of 7 is 1 to 7. Or the second branch is F of 1. So this is your second branch, and the second branch is tabulated. F of 1 is 1, F of 2 is 2, F of 3 is 1 to 3, F of 4 is 4, F of 5 is 1 to 7, F of 6 is 2 times F of 3, F of 7 is 1 to 7. So now, how many choices F of n takes? So F of 1 takes 1 choice, F of 2 takes 1 choice, F of 3 takes 7 choices, F of 4 1 choice, F of 5 7 choices, F of 6 can take 1 choice, F of 7 can take 7 choices. These are the number of choices what we have written. And here also, F of 1 can take 1 choice, F of 2 1 choice, F of 3 3 choices, F of 4 1 choice, F of 5 7 choices, F of 6 only 1 choice, F of 7 is 7 choices. So these are the number of choices F of n can take in the second branch. Now, the number of functions by product rule of counting is 1 into 1 into 7 into 1 into 7 into 1 into 7. So the number of functions is, so it is 7 into 7 into 7, that is 343. In the second branch, the number of functions by the product rule is 1 into 1 into 3 into 1 into 7 into 1 into 7, and that is 3 into 7 into 7, 3 into 49, that is 147. Now, by some rule of counting, the total number of functions satisfying the given conditions is this plus this by some rule, that is 343 plus 147, that is 390. That's your answer. So the total number of functions satisfying the given conditions that are given in the question is 390. And I am sure that you have understood the solution of this problem, and go on working out some more problems on these lines from the counting the number of functions. And I wish you all the best. Thank you.